Okay, now another very important concept are trend and seasonalities. So here you see a series that has an upward trend and seasonality, quite prominent seasonality. This it's actually one of the most well-known time series, air passenger time series. It's monthly numbers of air passengers in the US from, you see, the 1950s to the 1960s. Okay, and now we can decompose this series into a seasonal part, a trend part, and a remainder. And you see here, I did some data transformation on this series. It looks a bit different, right? So here the seasonality was kind of getting bigger, whereas here it's not. We get to that in a moment. But so basically I've decomposed the series with this method called STL. STL stands for seasonal trend decomposition using low S. And the way it works is you see here these little bars that are the same size in seasonal, trend, and remainder. Same size in the sense that, so if the bar is a lot smaller, that means that, for example, the trend component obviously is way bigger than the remainder component. Okay, so how does STL work? It's an iterative smoothing procedure. It first extracts the trend. It builds series for each component, then smoothes those, puts the series together, smoothes, and removes the seasonality. Actually, right now, I'm not too sure if it first removes the trend and then the seasonality or the other way around. But anyway, so it basically just smoothes the series iteratively to get these components, and it removes these components, and then it continues smoothing to remove the other components. Yeah. And another thing, another interesting tool is this season plot that you see on in the lower part here. So here we basically just take all the Januaries, we put them together. We take all the Februaries, put them together, all the March, put them together. Then we calculate the mean over that. These are these blue lines, and with that you can see kind of a seasonal pattern, average seasonal pattern, and you also see kind of this trend behavior that over the Januaries it goes up. But you see now this trend behavior, it has no seasonality anymore. So you have basically also kind of separated out trend and seasonality visually. Yeah. So when you hear in the news something about seasonally adjusted unemployment data, for example, then that's what they do. So they decompose the series, take out the seasonality, and then look at only the series with the trend. So there are methods that do decompositions using information from both the past and the future to calculate the decompositions. We've seen STL. There's a multi-seasonal version of it called MSTL. You have STR, that's seasonal trend decomposition using regression. And then you have more classic methods like the X11 ARIMA and the Tramoseed that are still, I think, the methods of choice by like national banks and so on. And now it is important to understand that many forecasting methods, they decompose the series as well into trend, seasonalities, and remainder, but it's a bit different here. So their goal is to extract components that are easier to predict, and they're easier to predict because they are smooth. But forecasting methods can only use information from one side, from the past, right? Because STL uses information to smooth. So for a particular point, it uses information from both future and past for its smoothing, whereas a forecasting method can only use the past data. So beware of data leakage in this context. You should never smooth, extract components from a whole time series before partitioning into training and test, right? Because STL uses data for each data point from the future and the past. So So a trend, if you cut the trend component, you would have used data from the future already in the past. One method, for whichever reason, I see that quite a lot in the literature as well, is a method called EMD, empirical mode decomposition, which also extracts very low frequency signals and then goes to higher frequency signals in the series. And there are published papers out there where they kind of extract these very low frequencies from the whole series, then they partition into training and test set, and then afterwards they predict these low frequent series, and they always get great results. But obviously that's data leakage. Okay, so yeah, speaking about forecasting methods that do decomposition, the most well-known of those is exponential smoothing, which is just this simple exponential smoothing that we've seen before, but applied to components, level, seasonality, and trends. So it decomposes a series and then runs simple exponential smoothing on these components. It was invented by Holt in 1957, together with his student Winters in 1960. That's why it's often called the Holt-Winters method. And it was used for a long time as a relatively ad hoc method without a theoretical underpinning. And then Hindman et al. In 2002 gave it a solid statistical foundation in state space models. And since then, we have this abbreviation ETS that stands both for exponential smoothing and as for error, trend, and seasonality, which are these components that ETS extracts. To give you an example, again using forecast package in R on our air passenger series, you just call ETS on the series, then you call forecast, and you call plot, and you get this forecast that looks relatively decent. It has some problems. We get to that in a moment, but yeah, very easy one-liner to do this forecast. If we just plot the model, the ETS model, this is what the plot gives us. It gives us these components that ETS has extracted. So top is the observed one, and then you have the level, you have the slope, and you have the seasonality that is extracted.